So we're continuing with Analytic Trigonometry, section 5.1. Yesterday we covered some basic identity functions, the idea that the sine of an angle is equal to 1 over the cosecant of the angle. We did the same thing for cosine, 1 over the secant of the angle. And we did the same thing for tangent, 1 over the cotangent of the same angle. And of course you can flip these back and forth, just like I've said when you're solving algebraic problems, you can switch the cosecant with the sine. We also then went to a basic identity for tangent and cotangent that said the tangent's the same as sine over theta divided by cosine over theta, and that cotangent of theta is equal to cosine over theta divided by sine over theta. So that's kind of what we covered yesterday. Oh, no, we also covered the Pythagorean Theorem identities. And these are the more interesting ones, that sine of theta squared plus cosine squared of theta equals 1. The big deal here was we write squared as sine squared, like sine with a little 2 above it, and cosine with a little 2 above it. The other one we got to is 1 plus tangent squared theta equals secant squared theta. There is a parallel that we did not get to yesterday, and that is 1 plus cotangent squared theta equals cosecant squared theta. Now, this one you can see is kind of parallel to the tangent one. 1 plus tangent squared equals secant squared. Instead of tangent, we use cotangent. Instead of secant, we use cosecant. I'll leave it to you to work out the details because I want to get to today's lecture. So that's from yesterday. If you need any of this from your notes, you've got to really look at yesterday's screen. Today, we're going to go on and look at something called the cofunction identity. So I'll slow down a little bit so you can start getting this in your notes. The interesting part about this is that it will explain why we call cosine cosine. And it all starts with a triangle. A right triangle. And normally, we've looked at, there's your theta. Instead of calling it theta, so I can keep it straight, I'm going to call this one A. But it's the same as if I called it X or theta or anything else. That's our angle right there. But I'm also going to label this angle B. Now, what I want you to notice is two things. First, your identities change depending on whether you're talking about angle A or B. To angle A, and I'll put this in red so we can see it, this is the opposite side. That's the adjacent side. To angle B, and I'll put this one in blue, this is the opposite side, and this is the adjacent side. In other words, depending on which angle you're starting with, you see the world in two different views. Which is your opposite side, depending on whether you're angle A or you're angle B. Both sides agree that this is the both angles agree that that's the hypotenuse.
So the opposite goes across from the hypotenuse, or
the angle you care about.
Okay.
So let's look at some of these. If I look at the sine of A, well, let me label these so we're consistent. I'm going to label this, go back to our normal labeling, and call this Y and X and R, right? That's kind of the consistent labeling we've done when we're talking about angle A. And the sine of A is Y over R. Same as what we talked about yesterday, what we've been talking about for weeks in the past. Cosine of A is X over R. Now I want to look at, I'm not going to change around the Y, the X, and the R. That's Y, that's X, that's R. That's our point. But I'm going to look at it now from angle B's perspective and say, well, what is the sine of B? Well, when B looks at it, B says, X is my opposite side. R is still the hypotenuse. So from B's standpoint, if you said, what's the sine of B? Opposite over hypotenuse. So katoa, it's now X over R. And if I said, what's the cosine of B? you would say, oh, well, that's the adjacent side, which in this case is y over r. If you're looking at this, you'll notice that the sine of A, right there, is exactly the same as the cosine of B. And the cosine of A is exactly the same as the sine of B. Exactly the same. Now, I said there are two things to notice about this triangle. I'm going to show you the other. Triangles all add up to 180 degrees. So if I added up all these angles, the A plus the B plus the right angle down there, I know that equals 180 degrees. If I take away the right angle from both sides of the formula, I know that A plus B has got to equal 90 degrees. Got to in a triangle, because they all add up to 180. Take away the right triangle. So I know the relationship between A and B. They're what we called in geometry complementary angles. Keyword being complementary. This is where the word cosine comes from. The cosine of an angle is the complement of the sine using the complementary angle. So if I find the sine of A, that's the same as the complementary sine of A, which we abbreviate and call cosine, except we're going to use the complementary angle. It's sort of like when you subtract a negative, you get a positive. When I use the complementary sine function, the and I use the complementary angle, B, I end up with exactly the same place. So we call these the cofunction identities, where co is kind of short for complementary functions. And here's what they say. Everyone got this in your notes okay? All right. Basically says this, and I'm going to write it the same way in the book. The sine of, now you can use either pi over 2 or 90 degrees, but I'll keep everything in degrees. The sine of 90 degrees minus an angle theta is equal to, let's get this out of the way, the cosine of theta. Or if you prefer, the sine of theta is equal to the cosine of 90 minus theta. In other words, whatever angle you're dealing with, the complementary sine of it, or the cosine, is equal of the complementary angle is going to be exactly identical. And that works for sine and cosine. And by the same logic, it works for tangent. So the tangent of 90 minus theta is equal to the cotangent of theta. And yeah, and the where they start with secant. I'm on page 447 in the book, by the way. The secant of 90 minus theta is equal to the cosecant, CSC, of theta. That's where all those cos came from. They're just saying, oh, you're going to switch over 90 degrees by subtracting the angle from 90, get the complementary angle, so use the complementary function, and everything will be the same. We're going to come back and work a few problems so you can, well, no, tell you what, I'll work one right now with it. Let's assume that, let's see, the cosine of theta, I've got some angle, and it's equal to 0.34. And the question is, can you find the sine of 90 minus that angle? And the answer is yeah. It's going to be exactly the same thing. I switched functions from the cofunction down to the sine, the cosine to the sine, but I also switched the angle from theta to 90 minus theta, and I know that's going to be exactly the same number. You know what? I'll explain it using the unit circle because it'll make even more sense on the unit circle. If you did the unit circle and you remember on the test that at 30 degrees, we were at the point square root of 3 over 2, 1/2. Remember that? So that's saying that the sine is 1/2 and the cosine is square root of 3 over 2, right? What's the complementary angle to 30 degrees? What's 90 minus 30? 60. Up here at 60 degrees, it was not a coincidence that these two numbers got switched. The sine of 30 is the same as the cosine of 60. 30 and 60 are complementary. So use the complementary function, in other words, switch to the other function, the one that's complementary with it, and you'll have exactly the same answer. So if cosine of 30 degrees is the square root of 3 over 2, and it is, then the sine of 60 degrees is also the square root of 3 over 2. In other words, the sine of 90 minus 30, which is 60, is going to be exactly the same number. Find the complement of the angle, use the complementary function, you'll get exactly the same. So we'll work a few more in a second, and I'll do it offline, and so I finish with the audio. Because there's, the one that has the word co in front of it, or take away the word co. Complementary functions all have the word co. Do you notice every one of these functions has sine, cosine, secant, cosecant, tangent, cotangent. Those are the ones that all pair up with each other, and that's the reason they call it cosine. Even and odd functions, the identities, these are easier, and it's the last ones, and then we'll just work problems, because I know you've got a lot of formulas now, and you'll just have to get used to how they work. All right, let's go back for a second. When we talked about even functions before, we talked about two things. One, they tended to be functions where all of the exponents were even. So x to the fourth minus 6x squared plus 2. That was an even function. Odd functions looked like this. They were like x cubed minus 5x. The exponents were all odd. And what made them interesting was when you graphed an even function, whatever crazy graph you had on the right side, you had exactly the same graph on the left side. This would be an example of an even function. If you had an odd function, whatever you had on the right side got rotated around, and it had rotational symmetry. Even functions had reflectional symmetry about the y-axis. And one more fact we learned about this is that if you plug in a value of x, so you get an f of x over here, and you plug in the exact same value except with a negative sign, it turns out they're equal to each other. So if I plug in a positive 1 and I get to this peak up here on my curve, when I plug in a negative 1, I get to the exact same peak. If I plug in a 3 and I'm down in this valley, when I plug in a negative 3, I'm down in the same valley. In other words, they're exact mirror images of each other. Even functions, whatever's on the right is exactly what's on the left, or f of x is the same as f of negative x. With odd functions, it was a little different. Whatever you plugged in for x, like if I plugged in a 2 and I'm in this flat section, when I plug in a negative 2, I'm down here, same value except the negative version. F of x is equal to negative f of negative x. Or the way they actually write it in the book, negative f of x is equal to, running out of space writing, equals f of negative x. In other words, putting in a negative value gives you the negative answer of what you had before. Now you may be saying, what's all this got to do with sines and cosines and so forth? It turns out that they are all even and odd functions. just the same way. So let's first take a look at the cosine function. If you look at the graph of the cosine function, it does this. This is the graph of the cosine function. That's an even graph. Whatever you get on the right side is exactly what you get on the left. They are mirror images, reflectional symmetry. And I can actually graph this on a graphing calculator so that you can see it. Y equals clear cosine x, zoom 7. And you can see the right side of the graph is exactly the same as the left side of the graph. Well, that's an even function. And what that means is the cosine of negative x and the cosine of x are exactly the same. So if you asked me, if you told me what the cosine of 40 degrees is, and it's going to be some number, I don't know what it is. You can punch it in your calculator and see. Whatever number that is, I can tell you you're going to get the exact same answer when you plug in negative 40 degrees. And let's just try it and see. Clear. Cosine 40 degrees, 0.766. Cosine of negative 40 degrees, quit. Yeah, let's plug in the right way. Cosine negative 40 degrees is 0.766. Same number. Cosine is what we call an even function. Sine, on the other hand, does something different. And so does the tangent function. We'll get to that. If I go back to my graph and I say, no, let's take a look at what the sine function, what it looks like. Zoom 7. Not quite. If you look at the left and the right, they aren't mirror images, but it's rotational symmetry. In other words, this right side, if I rotate it about the x-axis and just rotate it upside down and slide it over, whoops, it's rotated around. The sine function has rotational symmetry. Exactly, so it's an odd function, which means that negative f of x equals f of negative x. Put it another way, if I know that sine of 40 degrees is some number, when I plug in negative 40 degrees, I'm going to get the exact opposite sign. I'm going to get the opposite sign. That's a lot of negatives, so let's actually work it so you can see. Well, the negative actually goes over here, so I'll do it the way I wrote the formula. So I take the sine of 40 degrees, clear it out, clear. Sine 40 degrees, that's 0.64. Now I'm going to put a negative sign in front of it, and I'm telling you that when I plug in sine of negative 40 degrees, I am going to get negative 0.64. So they're just opposite signs. So sine of negative 40 degrees is negative. So in other words, plug in the sine of 40, put the negative sign in front of it, because it's negative sign, negative f of x. I get negative 0.642787. Sine of negative 40 degrees is also negative 64. Tangent turns out to also be an odd function. Maybe it's easiest to see on the graph. Clean sheet here. The tangent function, if I say y equals tan x and graph it, zoom 7. It's hard to see on some of these upward curves, but if you focus on the middle curve, you can see it looks kind of like the x cubed function. It's similar. So it turns out tangent is also an odd function, which means just like sine, negative tan x equals tan of negative x. And all the cofunctions are, they follow in suit too, but I'm not going to quiz you on that. They list them all.
So,
Mhm.
they're all odd functions or cosine's an even function?
Cosine's an even function, and it turns out secant's an even function too.
So those are the only ones that?
Yes. Cosine and secant turn out to be the only even functions, because secant's is the reciprocal of cosine, so it's going to be have the same properties as this 1 over. All right. All of this is tools so that we can play this elaborate thing called logic games with trig. And I'm going to go ahead and work a few problems with you right now so that you can see how this comes together. Start easy, and we'll go up depending on level of difficulty. Think of it as just a video game or an app where you're just going to use all of these rules that we've just written down to see if you can simplify. So here we go. First, I'm going to use one that involves the identity functions. Can you simplify sine of theta times cosecant of theta? Can you simplify that so that you don't have to deal with two different functions? Now this goes back to the identity. Look at what the identity is of sine or cosecant. Anyone? Okay, I'll tell you. What's that? Well, all right, what's sine equal to? So I can rewrite this as 1 over cosecant, and I can write this as cosecant. Now, here's the tricky part, and you have to just think about this. All of the rules of algebra still apply. And we're going to do some elaborate ones, even involving quadratic equations with trig functions, as bizarre as that sounds. But it all still works. 1 over cosecant times cosecant, just like in algebra, when you're multiplying fractions, these cancel out, and you're left with 1. Try another one. What is cotangent of theta times tangent of theta? Rewrite cotangent. If you don't see the identity, that's okay. You can always rewrite it as sine over cosine and cosine over sine. Because tangent is 1 over cotangent, or cotangent's 1 over tangent, whichever way you want to look at it, times tangent of theta. Again, the tangents cross out. Or maybe you go, I don't remember that, but I do remember that cotangent is cosine over sine, and tangent is sine over cosine. See how they cross out? Yeah. And again, these all cancel, and we get 1. No? Yes? Easy enough? Okay. All right, let's try another one. I'm not going to make it much harder. What would the tangent of theta times the cosine of theta equal? Can we simplify that one? Now, no identities are going to help you, because if you start turning any of that into cotangent or secant or anything like that, it's just not going to simplify. Here's my advice. Whenever you see tangent or cotangent or secant or cosecant, any of those, turn them back into sines and cosines and see what happens. So what's tangent equal to? Look in your notes. Okay, so let's replace it with sine over cosine. If I can get everything back into sines and cosines, it's a lot easier to see. It'd just be sine, right? Yeah, sine theta. Yeah, it'd just be sine. Oh, don't ever cross out the theta. The theta is kind of attached to the function. It's sine theta, cosine theta. and tangent theta. And yeah, it is snowing outside. Cool. Now, this is one we can actually test because my calculator has all three of these buttons. So give me your favorite number between 1 and 90. I heard 74. So I'll go tangent 74. I will multiply that times cosine 74. Was that the number, by the way? Okay. All right. So it's tan 74 times cosine 74. We're going to get a number. I don't know what it is. I don't really even care what it is, but it's 0.96. When I punch in sine of 74, same number. This works. Now, I've got to tell you, in your career, in your life, please write to me if you ever need to use this, because I doubt you will ever use this in your entire life. However, it is kind of cool to see that it works based on now what you know about tangents equal to sine over cosine, cosine. All it is a big logic game. Can I solve these, simplify them, and break them down? Does that one sound okay? How much harder do you want the next challenge to be? Okay, just a little bit. All right. What's sine theta times cosine theta times tangent theta times cotangent theta times secant theta times cosecant theta equal to? All right, there you go. Yeah, that's the idea. Every single one. If you multiply every single function that we've talked about together, guess what you get? Exactly. All right. They're all opposites, but let's just rewrite it in sine and cosine. So every time I come to one I don't know what it is, I will rewrite it as in terms of sine and cosine, because that'll make my life easier. Because I have no idea what a cosecant is, or secant maybe, or something. Cotangent is cosine over sine. Secant is 1 over cosecant. Cosecant is 1 over sine. Now I'll put these fractions over 1. I've taken, if you can, the one thing you've got to be able to do is turn every function into sines and cosines. So memorize the tangent is sine over cosine, or at least have it handy in your notes that you can look at it. Cotangent, the opposite. Secant is 1 over cosine. Remember, it doesn't have a co, it goes with a co. Cosecant has a co, so it goes with a non-co. So anyway, be able to convert all of them into sine and cosine, and now it's just a cross cancellation game. And it doesn't matter who you cancel with, it's just the sine up top cancels with the sine down below, cosine. Everything cancels out. You're left with 1. All right. I think you all are ready for a little tougher one. Yeah, you are. Yeah, you are. I know, we're almost done. We're almost finished with this. Okay. Sine cubed of x. Now you're probably going, sine cubed? I barely got a handle on sine squared. It just means sine times sine times sine times sine. I think I said that the right number of times. All right. It is a plus sign. I want you to think of this the same way you think of variables. If I told you I had 4x plus 4y, and I asked you to factor something out, you would just bring the 4 out front, and you'd be left with x plus y, right? Okay, we're going to do the same thing to this problem. What do they have in common? Well, that's got a bunch of sine x's, 3 of them multiplied together. That's got a sine x. We are going to simply bring out sine x out in front. All right, what are we left with? That's exactly right. That's what you're left with. Now check your notes. Sine squared plus cosine squared. So it's 1. Okay. And the answer is just sine x. You don't have to put 1. You could just jump right straight down to sine x is the answer. All right. I think we have done enough for one day because I'm sure I've made your head hurt. I will tell you what the homework's going to be, but I'm not going to make it due until Tuesday of next week. So you have tons of time, and I'm going to stop this recording.